Hello, everybody. My name is Ahmet Köse. I'm the co-founder of R8tech. My role also in this company is Chief Information Officer. Today, I will be talking about automated fault detection in HVAC systems with machine learning and rule-based methods. I would like to start with the energy consumption by sectors. Buildings account for 40% of energy-related CO2 emissions, and half of distribution comes through the commercial buildings. This is where R8 is taking a role. So we are mainly concentrated on ventilation, cooling, and heating systems in the commercial buildings, which may count approximately 6 to 7% of the energy-related CO2 emissions. Perhaps it's really important to start with our portfolio, which is actually directly linked to the fault detection or automated fault detection. So we started in the Imre-Gustav, Tallinn, Estonia, and in recent years, we expanded our portfolio towards Baltics, Nordics, and other parts of Europe, especially in South side. So as the pictures or the image suggest, we mainly focus on high quality or premium buildings as our clients. They do have a full equipped with the HVAC systems, and they do have a proper building automation system, which is centralized all the HVAC components. Another important fact is that I have to talk a couple of words at least about our product. R8 Digital Operator is a software-based solution which has no obligation in terms of the hardware components. So it doesn't require any sort of investment to building, which use existing infrastructure. It might be the Siemens or Niagara, Schneider, or Fidelix in terms of the automation systems. What we do is that we do read the information from the automation system in the 15 minutes intervals, and then we do start the monitoring the building, and then we do start the control, or let's say the writing or adjustments of the HVAC set points. So the solution works 7/24 with the main goal to ensure highly performing smart buildings, and we aim to follow three main KPIs: energy efficiency, comfortable indoor climate, and technical conditions. So under the light of the definition of the R8 digital operator and importance of the FTD in HVAC system should be taken into account. Our experience shows that the most important fact of the FTD has been so far, for us at least, is the health and well-being, which has to do a lot with the satisfaction of the occupants of or tenants about the indoor climate. It is also about the health-related problems. The second thing might be the really important is sustainability, or let's say the efficiency of the building itself. And it's directly with the fault detection and diagnostics. Another important point is about the tasks or the maintenance work about the HVAC systems. So typically, what has happened so far, or what's happening still, is that there are maintenance companies, they are doing their checks, or they are making their maintenance in some sort of intervals, might be the monthly, yearly, twice a year, etc. But nobody is certain, or nobody is really confident or sure that the fixes or the maintenance are in the most optimized, or that they are managed in the most optimized way. So another thing which is related to the issue is about the cost of the maintenance. Is the real cost, or the cost is actually that could be reduced a lot, even though nobody's aware of it. Important of the optimization through HVAC is that if the systems are not performing well, then this is not possible. The optimization is not possible here. Naturally, if we are increasing the efficiency of the building, then the property value will be increased as well. The life cycle of the HVAC components has a lot to do with the fault detection. And the last but not least, the most important point for us as well, enabling the control or the adjustments. In other words, if there are any mechanical failures of the HVAC system, it's not possible to control anything. I would like to continue with the building management systems, which is some sort of the user interface, or the concept is that bring the visualization of the building HVAC systems to the operators or technicians or the managers within the building. They are really important, especially to become as a smart building, but at the same time, they remain abstract and limited. The main reason for that, there are thousands of parameters to observe and calibrate for an operator. So in this regard, making the most optimal calibration is overcomplicated. There is no possibility of data-driven decisions or data-driven control in the frame of the building management systems. From the perspective of fault detection and diagnostics, the main sources for the faults are the BMS alarms, complaints, and coincidence in commercial buildings. I would like to emphasize the daily scenarios, at least one of them. Like, let's imagine how the operators are working in the commercial buildings. In the common cases, there are some sort of complaints comes to the tenants or occupants. Either typically is about the temperature, is it cold or hot, or it might be lack of air or some sort of smell. And then there is a call comes through the operator, and then the operator or technician goes on site. First they go to BMS, then they go to site. They do make some adjustments, or if the adjustments doesn't work, they go on site and try to do some fix or some change. And then there is like always like a calls between each other. There is already time consumed, and presumably something is fixed. But the main question is there, if the problem, the actual problem was solved or not. And then maybe the secondary question could be, how long did it take to find the problem and fix the problem? So if you're lucky, of course, you can directly see what might be the problem with the sensor or with the mechanical failure, but it's not the case in all the time. Controversially, from the R8 perspective, we aim to find the root cause at first place for the problem or the fault, and then we aim to give the reason or the concrete motivation of the problem there. What we could say is that automated fault detection starts with the digitalization. So as I mentioned previously, that there are building management systems, they are abstract, they have limited features for the operators to move on or to operate the building. In this building management systems, typically the heating, cooling, ventilation, and rooms are independent. In some events, in some commercial buildings, the room controllers are not connected to the BMS, or part of the heating or cooling circuits are not there. So the idea is that, as an example of ventilation, the return temperature could give some sort of indication about the temperature in the occupied areas, which is just the one indicator, but it doesn't give you the real picture or the full resolution. What we are aiming to do is that we aim to go through all the, let's say, the parent and child components. So which means that if there is some sort of heating circuit or cooling circuit, that we aim to connect with the components in terms of demand and response. If it's a heating radiator circuit, the radiator should be taking care with the connection. For the cooling, in the same manner. If there's a chiller or another fan coil circuit, should be going there, or the heating or cooling coils of the ventilation machines. In addition to that, there are also the building actual needs. It has to do with the tenant interactions. It has to do with the weather forecast, even if there is a market price to follow, and other elements of the ecosystem of the building. There, it is then possible to automate the fault detection. The architecture, the structure as it is, but then the content itself. So the building commissioning starts with design, and it goes to the operation level, maybe right after the BMS. So we aim also to follow the same approach. The idea is here to get the design information right from the source. So if you are lucky, if there is a beam information available, we do get the information about the connections, like it might be design or drawings, the connections between the old HVAC systems. At least we are able to get the technical parameters or the limitations of the mechanical systems through the design or the beam models. What gives to us is that we already know by this method what are the parameters when the fault detection should be already activated or triggered, that this is going to exceed the capacity of certain devices. And then if there is some sort of connection, we are already trying to prevent or trying to inform in advance what kind of subcomponents will be impacted by or when. The fault detection, automated fault detection, goes through with the pyramid. So in the first part or the first level of the pyramid could be the BMS alarms. They are typically designed according to as I mentioned, the design or the beam models or whatever is known from the building design. And then the second layer could be the reactive fault detection. It goes through the rule-based and learning phase, which is about machine learning already. But for us, the final approach is that the way, how do you deliver the problem? I mean, if we are talking about advanced fault detection algorithms, which is relying on the data processing, supervised or unsupervised learning, but then the important thing is that who is responsible for the faults, and then how you can call for an action the right or responsible people from the site. So that has to be it has to be clarified, and it has to be taken care as important as how the fault is discovered and then presented to clients. So in this regard, the fault detection and task management are in the balance. The first thing is about finding the fault, and then the understanding what is the root cause of the problem, where the problem is going to be impacted, and then presenting the problem. So here, what we are taking as a two main concern is about the energy and then indoor climate. And then this information that the faults are basically calculated or basically labeled by the energy or indoor climate the classifications, and it's just a given or delivered to the facility managers. So energy somewhat can be calculated. So what I'm trying to say is here that we do know what is the capacity, we do know what is the consumption or the power of the certain devices, and then we can do some sort of estimation range. It might be cumulative cost, it might be some sort of calculations and saying that, hey, there is a certain problem, if you don't fix it, it might cause you X amount of money or euros. But here is even more important, how much is impacting the indoor climate. So that was actually I was aiming to prepare to go through the indoor climate. There is still, at least in my opinion, there is still like a big question mark. What is the perfect building indoor climate? who is the one that deciding what should be the indoor climate? It might be in some scenarios, and again, referring to commercial buildings, in some cases, the occupants or tenants are the decision makers, or in some cases, there's a facility manager that has a certain goals with energy efficiency or indoor climate policy, which might be through the portfolio even. They are the ones that who are giving decisions. We have seen both cases in a number of countries, in number of buildings. But once this question is answered, or you understand that what could be the perfect or what could be the target indoor climate, the next thing is that what is the current situation or current status with the indoor climate itself. So let's consider that the facility manager provides some insights about the indoor climate policy. They might be following ASHRAE standards or European standards or portfolio policy with the indoor climate. Then you are presumably you will be ending up with the three categories. In some areas, the building has a good indoor climate based on the target. In some areas, it's in the boundary, and then there will be some areas that they are in red zone, let's say. So the question is now, why there is some sort of different the classifications of the indoor climate within the same building, and how we would pretend or how we can minimize the red zones here. So if we are a little bit going further with our processing the data, processing the indoor climate data, then we could say that there are areas which are not far from the green zone, or they are nearby yellow zone. So maybe it's not that as important as the boundaries, or the ones that where they are in the too hot or too cold situation. So here, as the graphs or the image presents that there are some belts around. So if certain areas are stuck with the, let's say 26, 27 degrees temperature, let's say this is an office or this is a shopping area, or vice versa, that there are some areas stuck with the or constant they are with 18 or 17 degrees, which is doesn't regardless of this is summer or is winter. So it's in the most cases those are the areas, if they're not really like I don't know, some sort of storage or some sort of areas that are not commonly used, but I'm still referring actively occupied areas, then we could say that those are the areas must be taken care of first. And then if you present the information in this way, then the facility managers also understand, like, okay, where the real problem actually lies. So the simple question, why the indoor climate in some certain areas is too cold or too hot, or if we are talking about CO2, why the CO2 level is too high compared with the rest of areas. This is all about the automated fault detection with the right packaging. So we are going through the data-driven faults, and then it might be up to 10 times more precise of the HVAC system fault detections. We are talking here some measurements. We are talking here the BMS alarms. We are talking about the some standards. But again, the best way to understand what is happening in the building is the data collected through the building dynamics, or collected through the entire available sensor information of the building. So by this regard, by this regard, we are able to reduce also the cost of the consumption or energy consumption, or like avoiding the waste of the energy consumption. So here I will say that some examples on the right side is available already, that if the room temperature is so high, and then if the fan coil is working, then there has to be certain problem with the fan coil or the circuit itself. Or if the room temperature is too cold, and then there is some sort of air handling unit, it's like the cooling coil, sorry, if the room temperature is too cold, then the heating coil might be leaking, and then the supply temperature is not achieving the set point, what's set there. And then if we do not have this data-driven decision, it's really hard to understand if we're not trending in proper way. It's really hard to understand how long this the leakage is there, and then what is the actual impact to the indoor climate. And the same, another example here is that if the room temperatures are too high, then it might be the case that the circuit, the cooling circuit, has some faults there. So there are like lots of the rule-based and also the data-driven decisions what we are having and what we are presenting to our clients. But once again, the main packaging is about the energy and then indoor climate labeling. So in general, our ultimate goal is to achieve the optimum indoor climate in all premises. There is the red crossed labels are about the operational efficiency. So it might be because of the inefficient operations, and it might be also because of the faults which exist in the HVAC systems. And then the curve over there is the design, the capacity or design efficiency. So what we are trying to do is that based on the target temperature or target indoor climate, we are trying to bring all the commercial buildings or all our clients' buildings to the design efficiency. It might not be there at first stage, but by the fixing the components, by the increasing the operational efficiency, they will be nearby, if not there on the curve. So maybe as important as delivering the fault detection is about transparency. So what we know so far is that if the information is only in the building management system, there are some alarms and then there are some bells are ringing, and then this information typically doesn't go to technical management level even. So it's impossible to say the portfolio management companies or the portfolio managers are not aware what is the real situation or real conditions of the buildings, what they own or what they have. And then this is really important. If they could know, probably they could react, they could create additional budget, or they could find the right maintenance companies to solve the problem, because this is really important for their property and also about the satisfaction of the tenants once again. So in this the pyramid, if we are able to provide the transparency, then the fixing of the problems or the real picture of the building will be available for all the labels or all the classes what we see here. Then everybody will be able to be working more efficiently, and then the performance of the management will increase much more. I would like to maybe, I'm coming to the end of the presentation, and I would like to go with one case study here. This is the building which was constructed in just if I'm not mistaken, 2018, which is rather large building. This is the courthouse, and it has almost 50,000 data points with almost 3,000 HVAC components. So the building, once we are looking at it, looks quite good. But at the same time, what was interesting fact is over there that we found nearly 1,000 faults and anomalies within let's say the half a year. So besides the adjustments of R8 digital operator, the faults and anomalies help a lot us to increase the energy efficiency, also to increase the level of the thermal comfort. So by doing that, we were able to also save the CO2 emissions or reduction of the CO2 emissions here. I would say that the 31.5% is a real number, and then in average, we are also having some sort of buildings are in the same level. So if you are talking about other clients or other buildings, more or less we are in somewhere around 20 to 30% of energy savings, and then increasing the thermal comfort at the same time. So I would like to conclude my presentation here with some facts or interesting numbers. That we are at the moment in the 15 countries, is mostly in Europe, and then we were found in 2017. At March 2021, we do have more than 700,000 meter squares as a portfolio size, and then we do have more than 2 million data points to process for the fault detection and then for our control algorithms. I would like to thank for your attention, and then I will be available for your questions. Feel free to ask. Thank you.